As a last unit in our study of interactions, I'd like to do the example of paramagnetism. Paramagnetism provides an example that's very interesting mathematically, but it's counterintuitive physically. And I think that when you see the end result of this, you're going to be rather surprised. So what I have in mind in particular is to talk about the two-state paramagnet. So I'm going to consider n spin 1/2 particles, and they're placed in a magnetic field, let's say a magnetic field that is oriented in the z direction. Now when this happens, each particle behaves like a little compass needle, and so each one is going to be aligned either parallel, each spin parallel to the magnetic field, or anti-parallel. Those are the only two choices. And so we call these little particles dipoles, and let's assume that there's no interaction between the dipoles, so they're not interacting with each other, they're only interacting with the magnetic field. So we call this an ideal paramagnet. So as I said, the spins can be aligned either up or down with respect to the axis of the magnetic field, which in this case we're calling the z-axis. And if I think about the potential energy of such a configuration, when a spin is aligned with the magnetic field, the potential energy associated with that configuration is minus mu times b, where mu is the magnetic moment of the spin, and b is the size of the magnetic field. In general, of course, it would be minus mu dot b, but in this case, of course, mu and b are aligned parallel. So this is for what we'll call it spin up, or we'll give it the up arrow. In the case where the spin is aligned anti-parallel to the field, the potential energy is equal to plus mu times b, and we call this configuration spin down. We use the down pointing arrow or negative spin, however you like to do it. And it's such that if I were to do the following, I'm more likely, the more energetically favorable configuration is for the spin to be parallel to the magnetic field. So if I want to flip that spin from spin up to spin down, it's going to cost me an energy equal to 2 times mu times b. So I can look at the total energy of this system of n particles, and I can write it as total energy is equal to mu times b times the difference between the number of up spins and the number of down spins. I can also write that as, because since n is equal to the number of up spins plus the number of down spins, I can write this as my total energy is mu times b times n minus 2 n spin up for my total potential energy. Next, we're going to define a quantity m called the magnetization. That's the total magnetic moment. If I take all the spins and I add up their magnetic moments, I get the total magnetization, and that is equal to mu times the difference between the number of up spins and the number of down spins. And I can also write that as minus mu divided by the size of the magnetic field. So the question becomes, how do the potential energy and the magnetic field depend upon temperature? Or I should say, the magnetization and the energy depend upon temperature. The way we do this is statistically. Let's first find the multiplicity of the system. So I can say, I'm going to keep n fixed. Each value of n up and mu and m define a different macro state. It's kind of like having n coins, either heads or tails. So I can write the number of macro states is going to be equal to, of course, the old binomial term, and up factorial divided by n minus n factorial. So this goes back to our first unit on probability. So for small systems, you can compute omega pretty readily. All you have to do, and then what you have to do, if I want to know the entropy of this situation, all I have to do is take Boltzmann's constant and multiply by the multiplicity. If I have something like 100 spins, well, I might need a computer generator to find the number of states and then compute the entropy. But in any case, this can be done. If you do this, what's going to result is a very interesting plot. I'm going to show you the way we do this. This is very interesting. Suppose I have 100 spins, okay? If all of them were pointed up, I'd have a spin of minus 100. So I would have if I took the ratio of the potential energy divided by mu times B, if they were all pointing up, I'd have a value of minus 100. If they were all pointing down, they would all have a value of plus 100. And obviously, if you had half up and half down, you'd be right here in the middle at 0. But suppose I were plotting, against that, I were plotting the ratio of the entropy to Boltzmann's constant. So S over K. And that'd be minus 50, that'd be plus 50. And I would have a curve that looks like this. Okay, that's not beautiful. Let's draw a little bit nicer, a little bit smoother. Okay, it should be symmetrical on both sides. So that's not beautiful drawing, but we'll go with it. So notice the largest multiplicity and thus the largest entropy are going to occur at an energy of 0, right? Where you have exactly as many spins pointing upwards as you do downwards. But let's just for interest, what's going to happen, by the way, once I reach this point, as I add more energy to the system, we find that we're going to see that the entropy decreases because there are fewer and fewer ways to arrange that many spins, that kind of configuration. If you want to compare this to when we did the Einstein solid, this is quite a bit different than what we found in the case of the Einstein solid. On the other hand, a more interesting way to look at this is, let's start. Suppose we start here. Suppose we start in a situation where all the spins were aligned upward. Spin up, positive spin. And notice what happens. So I'm down here, I'm at minimum energy, and let's suppose the system starts this way, and I increase the energy. Okay? It's still negative. The entropy versus energy plot, notice, is getting, as I go up this curve, is getting flatter and flatter until finally when I reach the top, the entropy is flat, is completely flat. Now, so what's happening is the energy is approaching 0. The slope is also approaching 0. And so this system is going to tend to absorb no energy. So at this point, half the dipoles point up, half of them point down. But now, let's say we add more energy to the system. Now weird things are going to happen. Because now the slope starts to be negative. And in fact, it gets larger and larger and larger negative. So what that's saying is, physically, as the slope becomes more and more negative, the system will spontaneously give up energy. So what that's saying is, anything near it that has a positive entropy versus energy would be able to take energy from this system. Okay. Well, what about the temperature? Well, the temperature is a function of energy. If half the dipoles point up and half of them point down, the total energy is normal and the system behaves normally. But remember, temperature goes as 1 over the slope of ds du or ds dE, energy. And so the temperature is going to increase as energy is added. However, if the energy is 0, as in this point, the temperature then has to approach infinity, which is pretty bizarre in and of itself. At that point, the system will readily give up energy to any other system that will take it. Any other system with a finite temperature. In other words, paramagnets are infinitely generous at this point. If we go to even higher energies, what's going to happen is the temperature becomes negative. Now this is truly bizarre. You probably learned somewhere when you learned about the absolute temperature scale that the Kelvin temperature, we couldn't even reach absolute 0. That's part of one description of the third law of thermodynamics. We'll talk about that later in the course. But the thought of going below into negative temperatures seems quite bizarre. Yet, there are examples where this actually happens. So in this case, negative temperatures behave as though they are actually hotter than positive temperatures, because they're giving up energy. As we know, according to the second law, energy is going to be transmitted from something at higher energy, higher temperature, to lower temperature. So negative temperatures are actually higher, or hotter, I should say, than positive temperatures. In fact, one way to think about it is in the following way. If I were to list temperatures, 10 kelvins, 1,000 kelvins, 100,000 kelvins, my temperature would go essentially through infinity to negative infinity, and then up to minus 1,000, minus 10, minus 1, minus 0.01. All along this line, it's getting hotter and hotter and hotter. So the hottest you can be is to be just slightly below absolute 0 in terms of a negative Kelvin. Well, take a little look at a plot. Looks something like this. And so this would be a plot of kT divided by mu times B, so the ratio of thermal energy to magnetic energy. And this is energy divided by N times mu times B. And of course, we're approaching 1, like so. So this is minus 20, let's say, and this is plus 20, and this is plus 1, and this is minus 1. So you can only get negative temperatures if the energy of the system is limited and the multiplicity decreases as the maximum energy is approached. Now, you might say, this sounds like something highly theoretical and could never happen. And when I tell you it happened, you might be expecting me to say, you know, this was shown sometime in the last few years. Well, much to my surprise, when I learned this, yes, this can happen. Yes, it was demonstrated, but it was demonstrated even before I was born. It was demonstrated in 1950. And it was demonstrated by these two guys, Purcell and Pound, who did a paramagnetic experiment with nuclear paramagnetism, not electrons. Let's talk about it. Let's talk about how something like this can occur. So in this case, with nuclear paramagnets, it's the nuclei, protons, that are the paramagnets, not the electrons, of course. So here's what happens. In some crystals, relaxation for nuclear dipoles, as they exchange energy with each other, can be much shorter than the relaxation time for nuclear dipoles to equilibrate in a crystal lattice. So on short time scales, on a really short time scale, we can find that dipoles behave like they're an isolated system with only magnetic energy. So you don't have any vibrational energy due to the lattice. It's only magnetic energy that you have to worry about. So this is what we do. We start experiment at any positive temperature, and the dipoles in this case are going to be aligned with the magnetic field. So here are my dipoles. They're all lined up with a magnetic field at some positive temperature. However, suppose I suddenly reverse the direction of the magnetic field. Immediately, so my magnetic field now is pointing down, but my dipoles are still pointing up. So I'm aligned anti-parallel to the field. This results in a situation where I have a negative absolute temperature. And indeed, Purcell and Pound did this experiment in 1951 using lithium nuclei in a lithium fluoride crystal. And sure enough, they were able to demonstrate that their sample reached a negative Kelvin temperature. Quite amazing. Okay, that's sort of a rather high-level argument about that. Let's look at an analytical solution for a problem such as this. Let's assume we have a very large number of dipoles and a large multiplicity. When I look for the entropy, I know that S over K is equal to the log of my multiplicity. So that's going to be log of n factorial minus the log of the number of up spins, factorial, minus the log of the number of down spins, factorial. And I can use Stirling's approximation, so this is n log n minus n. This is minus n up log n up plus n up. This is minus n down log n down plus n down. Using Stirling's approximation, this is the log of n factorial approximation. This is a pretty good approximation. We're talking about very high spins. If I do that, I know that these terms, I don't have to worry about these terms. And what I can find then is that I can use this expression, write it in this way, n log n minus n factorial log n, n up log n up minus n up log n minus n up. I can use this to find the temperature. I can say 1 over T is equal to K over 2 times mu times B times the log of N minus mu over mu B divided by N plus mu over mu B. Notice, temperature and energy are always going to have opposite signs. Put this all together, and I can get U is equal to N times mu times B, if I rearrange terms, times 1 minus e to the 2 ub over kt, divided by 1 plus e to the 2 ub over kt. Again, a ratio of the magnetic energy to the thermal energy. Of course, I can write this more simply as my energy is equal to minus n mu b times the hyperbolic tangent of mu b over kt. It's a standard two-state system for spin. My magnetization, by the same token, can be written as n mu times the hyperbolic tangent of ub over kt in a similar way. Let's get a better feel for what this is. Notice, if I were to plot, suppose I plotted a hyperbolic tangent function. It would look something like this. Zero minus 1 plus 1, and so on. So this would be a hyperbolic tangent of x as a function of x. So it rises from the origin essentially, well, probably write it a little bit cleaner this way, with a slope of plus 1. Now, so the way this works is it flattens to an asymptotic value of 1 as the argument approaches infinity from the right side, going left to right. So at small positive temperatures, the system's completely magnetized. But as T approaches infinity, the magnetization approaches 0. So to get negative temperatures, all we have to do is give the system a negative magnetization, and I can get negative temperatures. By the same token, the heat capacity at constant magnetic field can be written, of course, as the derivative of the energy with respect to temperature at constant field and constant number, and that's going to be Nk times ub over kt squared divided by the hyperbolic cosine squared of mu b over kt. So we approach 0 at both high and low temperatures. And just to sort of finish the thought, so that all works with nuclear. What about electrons? Electron paramagnetism is caused by unpaired spins in a dipole field or in a magnetic field. We define a Bohr magneton for electrons is equal to E times H divided by 4 pi mc, and that's equal to 9.274 times 10 to the minus 24 joules per Tesla, if you like SI units, or 5.788 times 10 to the minus 5 electron volts per Tesla, if you like smaller units. So if magnetic field, in this case for electrons, if magnetic field is about 1 Tesla, U times B is going to be something like 5.8 times 10 to the minus 8 electron volts. Room temperature, by the way, if you're keeping track, room temperature is about on the order of 1 over 40 electron volts. So at ordinary temperatures, let's say a few kelvins, mu b over kt is going to be much, much less than 1. And when that happens, my magnetization is going to be something like n u squared b over kt. So what this shows is that the magnetization is proportional proportional to 1 over the temperature. And this has been proved experimentally, I guess the first time by Pierre Curie, and we call this notion of magnetization being inversely proportional to temperature as Curie's law. Now, if we were to do this with nuclei, the magneton for nuclei is 2,000 times less than that for the electron. So if I wanted to see an effect like this, I've got to have a magnetic field that's 2,000 times larger, or make the temperature 2,000 times less. So this is a really nice example of, it's a slightly different interaction, but a nice way to take our statistical analysis of interactions in a two-state paramagnet. We will see this example several more times. Thank you.